So the thing to notice about in this section is that we're dealing with the electric force, sometimes called the Coulomb force or the electrostatic force, and its form is very similar to the gravitational equation in that we've got this 1 over r squared dependency, and it depends on a single property of the material. In this case, it depends on the charge, Q1 and Q2, where these charges are typically measured in coulombs. That's just a measure of charge. In the case of the gravitational force, we had mass dependence here. So, as with the gravitational force, we've got the same definition for R. The electric force on 2 by 1 is a vector that's pointing from 1 towards 2. And unlike in the gravitational case, we don't have that minus sign out front. And that's because the sign of the charge is going to take care of the direction of the force. In the case of the gravitational force, we only had positive masses, and that force was an attractive force. In the electrostatic case, when the charges are both positive or both negative, we're going to have a repulsive force. So that's one difference between this case and the gravitational case. Now this 1 over 4 pi epsilon naught, that's just a constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. And I just wanted to comment a little bit that this constant here really is just kind of a unit conversion. It's converting between measurement of meters, coulombs, into newtons. And a lot of constants tend to be just unit conversions. Capital G is another example. It's basically relating these distances and masses to the force that's exerted. Another example, little g, which is just a relationship between the mass in kilogram and the force in Newton. Now, in some cases, like the speed of light, that's not a conversion, but an actual property of this system. Anyway, the key to this section really is just noticing the similarities to the gravitational force and being able to use a lot of the skills that you've used with the gravitational force in this case.